Welcome back to our course on computer organization and architecture. We're going to continue in this lecture in this second major section that we have in our textbook. And so we got a nice introduction of a top level view of computer function and interconnection. And now we're going to have several lectures on memory. So this is going to be the first one. And we'll first of all, with this chapter and this lecture, talk about memory hierarchy. So that's the focus. And so in terms of the contents here, we'll come back to this at the very end as a reminder, but we'll be talking about how memory actually starts to look in the computer if we will start to measure that. And there have been some examples here of doing different studies that have been given this kind of information to help us along here. So we'll be talking about the principle of locality, characteristics of memory system, performance modeling at a multi-level memory level. And so this is something that we'll talk about two-level and multi-level. And then we'll finish up with the memory hierarchy, cost and performance characteristics, typical members of the memory hierarchy. We'll give an example with an IBM Z13 memory hierarchy. And finally, design principles for a memory hierarchy. So let's start out, have a couple charts on the principle of locality. One of the most important concepts related to computer systems is the principle of locality, also referred to as the locality of reference. The principle reflects the observation that during the course of execution of a program, memory references by the processor for both instructions and data tend to cluster. So that's the important concept, that if we know that, we can take that into part of our design and use that in our architecture. Programs typically contain a number of iterative loops and subroutines. Once a loop or subroutine is entered, there are repeated references to small sets of instructions. Similar operations on tables and arrays involve access to a cluster set of data words. Over a long period of time, the clusters in use change, but over a short period of time, the processor is primarily working within fixed clusters of memory references. So that's, like I said, is one of the things we can take advantage of. We can put these observations more specifically, and as discussed in section 4.3, for different types of memory, memory is accessed and retrieved in units of different sizes, ranging from individual words to large blocks of cache memory to much larger segments of disk memory. And so these are the things that we're trying to explore. So let's talk about a couple of things here. In terms of locality is based on three assertions. During an interval of time, a program reference memory location non-uniformly. That is, some units of memory are more likely to be accessed than others. So we've already referred to that a little bit here. Number two, as a function of time, the probability that a given unit of memory is referenced tends to change slowly. But another way, the probability distribution of memory references across the entire memory space tends to change slowly over time. And third, the correlation between immediate past and immediate future memory references patterns is high and tapers off as the time interval increases. Intuitively, the principle of locality makes sense. Consider the following line of reasoning. Except for branching and call instructions, which constitute only a small fraction of program instructions, program execution is sequential. Hence, in most cases, the next instruction to be fetched immediately follows the last instruction set. Number two, it is rare to have a long, uninterrupted sequence of procedure calls followed by a corresponding sequence of returns. Rather, a program remains confined to a rather narrow window of procedure invocation depth. Thus, over a short period of time, references to instructions tend to be localized in a few procedures. Number three, most iterative constructs consist of a relatively small number of instructions repeated many times. For the duration of the iteration, computation is therefore confined to a small contiguous portion of a program. And number four, in many programs, much of the computation involves processing data structures such as arrays or sequence of records. In many cases, successive references to these data structures will be closely located data items. So that's the first couple of things we want to be talking about. Now let's get into a couple forms of locality, temporal and spatial. So a distinction is made in the literature between two forms of locality. First of all, temporal locality, it refers to the tendency of a program to reference to the near future those units of memory referenced in the recent past. For example, when an iteration loop is executed, the processor executes the same set of instructions repeatedly. Constants, temporary variables, and working stacks are also constructs that lead to this principle. And then number two, spatial locality refers to the tendency of a program to reference units of memory whose address are near one another. That is, if a unit of memory X is referenced at time T, it is likely that in the range K minus X minus K through X plus K will be referenced in the near future for a relative small value of K. This reflects the tendency of a processor to access instructions sequentially. Spatial location also reflects the tendency of a program to access data location sequentially, such as when processing a table of data. So here we have a figure that hopefully will start to shed some insight here. A crude analogy may help illustrate the distinction between these two concepts. So we look at here at figure 4.1. Suppose that Bob is working in an office and spends much of his time dealing with documents in the folders. Thousands of folders are stored in file cabinets in the next room. And for convenience, Bob has a file organizer on his desk that can hold a few dozen files. When Bob is working on a file and temporarily is finished, it may be likely that he will need to read or write one of the documents in that file in the near future, so he keeps it at his desk in his desk organizer. This is an example of exploiting temporal locality. Bob also observes that when he retrieves a folder from the file cabinet, it is likely that the near future he will need access to some of the nearby folders as well. So he retrieves the folders he needs plus a few folders on either side at the same time. This is an example of exploiting spatial locality. Of course, Bob's desktop file organizer soon fills up, so when he goes to retrieve a folder from the file cabinet, he needs to return folders from his desk. Bob needs some policy for replacing folders if he focuses on temporal locality. Bob could choose to replace only one folder at a time on the reasoning that he might need any of the folders currently, so his desk in the near future. So Bob could replace perhaps the folder that has been on the desk the longest, or the one that has had one of the longest, or the one that had the least recently used. So he's just trying to think logically about how he's going about that. So if Bob focuses on the spatial locality when he needs a folder not on his desk, he would return and refile all the folders on the desk and retrieve a batch of contiguous folders that includes the one that he needs, plus other nearby folders sufficient to fill up his desktop organizer. It is likely that neither policy is optimum. In the first case, he might have to make frequent trips to the next room to get one folder he doesn't have, but which is near one he does have. In the second case, he might have to make frequent trips to the next room to get a folder that he just recently put away. So perhaps a policy of returning and retrieving in batch equal to 10% or 20% of his desktop capability would be closer to optimal. For cache memory, which is something that we'll get a chance to talk about in some future chapters, temporal locality is traditionally exploited by keeping recently used instructions and data values in cache memory and by exploiting the cache hierarchy. Spatial locality is generally exploited by using larger cache blocks and by incorporating prefetching mechanisms, that is, fetching items of anticipated use into the cache control logic. Over the years, there have been considerable research on refining these techniques to achieve greater performance, but the basic strategies remain the same. Okay, let's have a couple figures that hopefully will give some insight into what we're talking about here. First, in figure 4.2, it provides a rough depiction of the behavior of programs that exhibit temporal locality. For a unit of memory across access at time t, the figure shows the distribution of probability of the time of the next access to the same memory unit. So there's a dropout. Now in figure 4.3, we have something that provides a rough depiction of the behavior of programs that exhibit spatial locality. For spatial locality, the probability distribution curve is symmetric around the location of the most recent memory access address. Many programs that exhibit both temporal and spatial locality for instructions and data access. It has been found that data access patterns generally show a greater variance than instruction patterns. So figure 4.3 suggests the distinction between the distribution of data across access, read and write that is, and instruction fetch addresses. Typically, each instruction execution involves fetching the instruction from memory and during execution, accessing one or more data operands from one or more region of memory. Thus, there is a dual locality of data's spatial locality and instruction spatial locality. And of course, temporal locality exhibits the same dual behavior, data temporal locality, instruction temporal locality. This is when an instruction is fetched from a unit of memory. It is likely that in the near future, additional instructions will be fetched from the same memory unit. And when a data location is accessed, it is likely that in the near future, additional instructions will be fetched from the same memory unit. Okay, here's another figure that an example of data locality is illustrated here in figure 4.4 that shows the results of a study of web-based document access patterns where the documents are distributed among a number of servers. In this case, the unit of access is a single document and temporal locality is measured. The access scheme makes use of a document cache at the browser that can temporarily retain a small number of documents to facilitate reuse. The study covered 220,000 documents distributed over 11,000 servers. As shown in this figure, only a very small subset of pages incorporates a high number of references, while most documents are accessed relatively infrequently. So those are some helpful statistics for us to be figuring out how we're going to be designing our memory architecture. In this figure, it shows an example of instructions locality based on executing the integer benchmark program in the spec CPU 2006 benchmark suite. And remember, we talked about this in chapter 2 when we were talking about benchmarking. So similar results were obtained for floating point programs. The following terms are used in the plot. Static instruction, dynamic instruction. So let's, first of all, static instruction is an instruction that exists in the code to be executed. Dynamic instruction, this is an instruction that appears in the execution trace of a program. Thus, each static instruction is represented by 0 or more instances of dynamic instructions when the program is executed. Each line in the graph represents a separate benchmark program. In the figure, the cumulative percentage of dynamic instruction execution by a program is shown by the y-axis, and the cumulative count of the static instruction is shown by the x-axis. The first point in the line for each benchmark represents the most frequent called subroutine, with the x-coordinate showing the number of static instructions in the routine, and y-coordinate showing the percentage of dynamic instruction that it represents. The second, third, fourth, and fifth points represents the top 5, 10, 15, and 20 most frequent called subroutines. Many programs initially show a steep upward climb, and so we're seeing that kind of trend here as the static instruction count increases, which suggests very good instruction locality. So the complex subject of computer memory is made more manageable if we classify memory systems according to their key characteristics. The most important of these are listed in table 4.1. So it would be useful for you to be going through the textbook and following this, but what we have here is a location, the capacity, unit of transfer, access method, performance, physical type, physical characteristics, and organization. So let's talk about the characteristics of memory system. The term location in table 4.1 refers to whether memory is internal and external to the computer. Internal memory is often equated with main memory, but there are other forms of internal memory. The processor requires its own memory in the form of registers. Further, as we shall see, the control unit portion of the processor may also require its own internal memory. We will defer discussion of these latter two types of internal memory to later chapters. Cache is another form of internal memory. Internal memory consists of peripheral storage devices such as disk and tape that are accessible to the processor via I/O controller, input and output controllers. An obvious characteristic of memory is its capacity. For internal memory, this is typically expressed in terms of a byte. 1 byte equals 8 bits, or words. Common word lengths are 8, 16, or 32 bits. External memory capacity is typically expressed in terms of bytes. A related concept is the unit of transfer. For internal memory, the unit of transfer is equal to the number of electrical lines into and out of the memory module. This may be equal to the word length, but is often larger, such as 64, 128, or 256 bits. To clarify this point, consider three related concepts for internal memory. First of all, word. The natural unit of organization of memory, the size of a word is typically equal to the number of bits used to represent an integer and to the instruction length. Unfortunately, there are many exceptions. And so a Cray 960, which is an older model of Cray supercomputers, had a 64-bit word length, but used a 46-bit integer representation. The Intel 86 architecture had a wide variety of instruction lengths expressed as multiples of bytes and a word size of 32 bits. We can be thinking of addressable units. In some systems, the addressable unit is the word. However, many subsystems allow addressing at the byte level. In any case, the relationship between the length in bits A of an address and the number n of addressable units is 2 to the A is equal to n. For the number of transfer, for main memory, this is the number of read out or written into memory at a time. The unit of transfer need not equal a word or an addressable unit. For external memory, data are often transferred in much larger units than a word, and these are referred to as blocks. Okay, here we have a table that's trying to give us a summary of the methods of accessing units of data. And so let's take this one at a time. First of all, for sequential access, memory is organized into units of data called records. Access must be made in a specific linear sequence. Stored addressing information is used to separate records and assist in the retrieval process. A shared read-write mechanism is used, and this must be moved from its current location to the desired location, passing and rejecting each intermediate record. Thus, the time to access an arbitrary record is highly variable. Tape units discussed in Chapter 7 are sequential access. Next, we have direct access as a sequential access. Direct access involves a shared read-write mechanism. However, individual blocks or records have a unique address based on physical location. Access is accomplished by direct access to reach a general vicinity plus sequential searching, counting, or waiting to reach its final location. Again, access time is variable disk units discussed in chapter 6 are direct access. So you're seeing that we're talking about some concepts, and then we're going to be having some more deep discussions as we move forward in the course. Next, we have random access, and so each addressable location in memory has a unique physical wired-in addressing mechanism. The time to access a given location is independent of the sequence or prior accesses and is constant. Thus, any location can be selected at random and directly addressed and accessed. Main memory and some cache systems are examples of random access. Finally, we have associative. This is a random access type of memory that enables one to make a comparison of desired bit location within a word for a specified match, and to do this for words simultaneously. Thus, a word is retrieved based on a portion of its content rather than its address. As an ordinary random access memory, each location has its own addressing mechanism, and retrieval time is constant, independent of location or prior access patterns. Cache memory may employ associative access. So that's a summary of those different types. Now let's talk about capacity and performance. And so from a user's point of view, the two most important characteristics are capacity and performance. These performance parameters are used: access time, memory cycle time, and transfer rate. Access time is for random access memory, this is the time it takes to perform a read or write operation. That is the time from the instant that an address is presented to the memory to the instant that data have been stored or made available for use. For non-random access memory, and access time is the time it takes to position the read-write mechanism at the desired location. For memory cycle time, this concept is primarily applied to random access memory and consists of the access time plus any additional time required before a second access can commence. This additional time may be required for transients to die out on signal lines or to regenerate data if there are if they are read destructively. Note that memory cycle time is concerned with the system bus, not the processor. And finally, we have transfer rate. This is the rate at which data can be transferred in or out of a memory unit. For random access memory, it's equal to 1 over the cycle time. Okay, let's talk about the variety of different types of memory that exist. And so there are a variety of physical types of memories that have been employed. The most common today are semiconductor memory, magnetic surface memory used for disk and tape, and optical and magneto-optical types of memory. Several physical characteristics of data storage are important. In a volatile memory, information decays naturally or is lost when electrical power is switched off. In a non-volatile memory, information once recorded remains without deterioration until deliberately changed. No electrical power is needed to retain information. Magnetic surface memories are non-volatile. Semiconductor memory, that is memory on integrated circuits, may be either volatile or non-volatile. Non-erasable memory cannot be altered except by destroying the storage unit. Semiconductor memory of this type is known as read-only memory, or ROM. Of necessity, a practical non-erasable memory must also be non-volatile. For random access memory, the organization is a key design issue. In this context, organization refers to the physical arrangement of bits to form words. The obvious arrangement is not always used, as will be explained in chapter 6. Okay, what about memory hierarchy? The design constraints on a computer's memory can be summed up by 3 questions: how much, how fast, and how expensive. Each one of those things are going to be drivers. And so as we're talking about in this course, we're talking about architecture and organization. And so we can be thinking about how we would go about doing a design. The question of how much is somewhat open-ended. If the capacity is there, applications will likely be developed to use it. The question of how fast is in a sense, easier to answer. To achieve greater performance, the memory must be able to keep up with the processor. That is, as the processor is executing instructions, we would not want it to have to pause waiting for instructions or operands. The final question must be considered for practical systems. The cost of the memory must be reasonable in relationship to the other components. As might be expected, there is a trade-off among these three key characteristics of memory: capacity, access time, and cost. A variety of technologies are used to implement memory systems, and across the spectrum of technologies the following relationships hold. Faster access time, greater cost per bit. Greater capacity, smaller cost per bit. Greater capacity, slower access time. The dilemma facing the designer is clear. The designer would like to use memory technology that provides for large capacity memory, both because the capacity is needed and because the cost per bit is low. However, to meet performance requirements, the designer needs to use expensive, relatively lower capacity memories with short access time. So that's where we get into these different types of memory that you could be using multiple in a computing capability. The way out of this dilemma is not to rely on a single memory component or technology, but employ a memory hierarchy. And so that's what we're showing with this figure here. So as one goes down the hierarchy, the following occurs: A, decreasing cost per bit, increasing capacity, increasing access time, decreasing frequency of access of the memory by the processor. And so those are the things that we need to be thinking about. Magnetic tape would probably be great, but it's not going to be something very responsive. CPU is going to be very responsive, but it's going to be very expensive. So those are the kind of things that we need to be considering. So here in figure 4.7, in a general way, and it's not per scale to scale, illustrates these relationships across the memory hierarchy. The smaller, more expensive, faster memories are supplemented by larger, cheaper, slower memories. The key to the success of this organization, item D, decreasing frequency of access, which can be achieved by exploiting the principle of locality, which we talked about in section 4.1. We discussed techniques for exploiting locality in the treatment of the cache in chapter 5. And so that's something we can look forward to in virtual memory in chapter 9. A general discussion is provided at that point. It is possible to organize data across a hierarchy such that the percentage of accesses to each successfully lowered level is substantially less than the one level above it. And so that's what we wanted to be thinking about. Another criteria for how we're going to be doing our computing organization and architecture development. So here we have a figure looking at the performance of a simple two-level memory. Suppose that the processor has access to two levels of memory. Level 1 contains X words and has an access time of 0.00 microseconds. Level 2 contains 1,000 times X words and has an access time of 0.1 microsecond. Assume that if a word to be accesses in level 1, then the processor accesses it directly. If it's in level 2, the word is first transferred to level 1 and then accessed by the processor. For simplicity, we ignore the time required for the processor to perform to determine whether the word is in level 1 or level 2. So in this figure, figure 4.8, it shows the general shape of the curve that covers this situation. The figure shows the average access time to a two-level memory as a function of the hit ratio H, where H is defined as the fraction of all memory accesses that are found in the faster memory, that is the cache. T1 is the access time to level 1, and T2 is the access time for level 2. As can be seen, For higher percentage of a level 1 access, the average total access time is much closer to that of level 1 and to that of level 1 than that of level 2. In our example, suppose 95% of the memory access are found in the level 1. Then the average time to access a word can be expressed in an equation that is in the textbook. I'm not going to go through that here. So anyway, we have a couple things that might be helpful to give you some more insight as we're looking at this graph. So this principle can be applied across more than 2 levels of memory. And we're going to be seeing this as we move forward. As suggested by the hierarchy figure in figure 4.6, in practice, the dynamic movement of chunks of data between levels during program execution involves registers 1 or more level of cache, main memory, and virtual memory stored on a disk. This is shown in this figure, figure 4.9, with an indication of the size of the chunks of data exchanged between each level. So in this table, 4.2, we list some of the characteristics of key elements of the memory hierarchy. The fastest, smallest, and most expensive types of memory consists of the register internal to the processor. Typically, a processor will contain a few dozen types of registers, although some machines contain hundreds of registers. Next will be the typical multiple layers of cache, level 1 cache, or L1 cache closest to the processor registers, almost always divided into instruction cache and the data cache. This split is also common for L2 caches. Most contemporary machines also have an L3 cache and some have an L4 cache. These 2 caches generally are not split between instructions and data and may be shared by multiple processors. Traditionally, cache memory has been constructed using a technology called static random access memory or SRAM. More recently, higher levels of cache on many systems have been implemented using embedded dynamic RAM or EDRAM. So those are just a couple memories that are out there that we can encounter. So main memory is the principal internal memory system of the computer. Each location in a main memory has a unique address. Main memory is visible to the programmer, whereas cache memory is not. The various levels of cache are controlled by hardware and are used for staging the movement of data between main memory and processor registers to improve performance. So let's talk more in detail about memory. The 3 forms of memory just described are typically volatile, employed semiconductor technology. The use of 3-level exploits the fact that semiconductor memory comes in a variety of types, which differ in speed and cost. Data are stored more permanently on external mass storage devices, of which the most common are hard disk and removable media, such as removable magnetic disk tape, removable magnetic disk tapes, and optical storage. External non-volatile memory is also referenced to as secondary memory or auxiliary memory. These are used to store programs and data files and are usually visible to the programmer only in terms of files and records, as opposed to individual bytes or words. Disk is also used to provide an extension to the main memory, known as virtual memory, which is discussed in Chapter 9. Other forms of secondary memory include optical disk and flash memory. So here we have an example for the IBM Z13 memory hierarchy. So now we're looking at a specific instance of a design. L1 and L2 caches use SRAM. We briefly mentioned that already on our private for each core. L3 caches uses EDRAM and is shared by all 8 cores with the PU chip. Each CPC drawer has 6 L3 caches, a 4 CPC drawer system, therefore has 24 of them, resulting in 1536 megabits, which is 24 times 64 megabits of this shared PU chip level cache. L4 cache also uses eDRAM and is shared by all PU chips on the node of a CPC drawer. Each L4 cache has 480 megabytes for previously owned and some recent and some least recently used LRUs, L3 owned lines, and 224 megabits for non-data inclusive coherent, non-data inclusive coherent, or NIC directory that points to the L3 owned lines that have not been included in L4 cache. So those are just some of the specifics here. I won't continue to be reading all this in details. The main storage has up to 2.5 terabyte addressable memory. The secondary memory holds the virtual memory and is stored in disk accessed by the various I/O technologies. So the design principles for a memory hierarchy are locality, inclusion, and coherence. So for locality, the locality is a principle that makes effective use of the memory hierarchy possible. We got a chance to talk about that in detail. Inclusion, this is the principle dictates that all information items are originally stored in level MN, where N is the level most remote from the processor. During the processing, subsets of MN are copied into MN-1. Similar subsets of M-1 are copied into M-2 and so forth. And then finally, for coherence, copies of the same data unit and adjacent memory levels must be consistent. If a word is modified in the cache, copies of that word must be updated immediately or eventually at all higher levels. Coherence has both vertical and horizontal implication and is required because multiple memories at one level may share the same memory at the next higher or greater level of I level. For example, the IBM Z13, 8 L2 caches share the same L3 caches and 3 L3 caches share the same L4 cache. This leads to two requirements, vertical coherence and horizontal coherence. So you can see there's a lot of details that are part of this when we're trying to figure out a memory hierarchy. For two-level memory access, so in this chapter, reference is made to a cache that acts as a buffer between main memory and processor, creating a two-level internal memory. In the simplest case, rarely implemented in modern systems, there is a single level of cache to interact with main memory. This two-level architecture exploits locality to provide improved performance over a comparable one-level memory. The main memory cache mechanism is part of a computer architecture implemented in hardware and typically invisible to the operating system. There are two other instances of two-level memory approach that also exploit locality, and that are at least partially implemented in the operating system, virtual memory and the disk cache. Virtual memory is explored in chapter 9. Disk cache is beyond the scope of this book, so we won't be getting into that in detail. So that's a quick little perspective on that. Now let's talk about the operation of two-level memory. The locality properties can be exploited in the form of two-level memory. The upper level memory M1 is smaller, faster, and more expensive per bit than the lower level memory M2. M1 is used as a temporary storage for part of the content of the larger M2. When a memory reference is made, an attempt is made to access the item in M1. If this succeeds, then a quick access is made. If not, then a block of memory location is copied from M2 to M1, and the access then takes place in M1. Because of locality, once a block is brought into M1, there should be a number of accesses to locations in that block, resulting in fast overall service. Here we have a figure showing the relationship of average memory cost to relative memory size for a two-level memory. So you can feel free to pause and look at that as long as you would like. Here we have another figure that shows the access efficiency as a function of the hit ratio. So another useful figure to ponder. And finally, here we have a figure that shows the hit ratio as a function of relative memory size. And so this figure suggests that the effect that locality has on the hit ratio. Does a relative size of the two memories satisfy the cost requirement? The answer is clearly yes. If we need only a relatively smaller upper level memory to achieve good performance, then the average cost per bit of the two level of memory will approach that of the cheaper lower level memory. So that would be a good result. Here, this figure 414 is a flow chart that provides a simplified memory access model for a memory hierarchy, which we can use to develop a formula for the average access time. It can be described as follows. Number one, the processor generates a memory address request. The first step is to determine if the cache block contains that address resides in the L1 cache. That is the memory level M1. The probability of that is H1. If the desired word is present in the cache, the word is delivered to the processor. The average time required for this operation is T1. For subsequent levels Ti, 2 less than or equal to I, less than N, if the address word is not found in Mi minus 1, then the memory management hardware checks to determine if the Mi minus 1, which occurs with a probability of H1. If the desired word is present in M1, the word is delivered from Mi to the processor, and the appropriate size block containing the word is copied to Mi minus 1. The average time for this operation is Ti minus 1. In the typical memory hierarchy, Mn is the disk used in a virtual memory scheme. And in this case, if the word is not found in any of the preceding levels and is found in Mn, then the word must be first moved as part of the page into main memory, Mn minus 1. From there, it can be transferred to the processor. We designate the total time for the operation as Tn. So looking at figure 414, there are a number of different paths from start to finish. So hopefully that explanation gave a little bit of clarity there. You can always look at the text and see some more details. All right, well, we're finishing up here. We talked about this during the introduction. We went into detail of talking about the principle of locality, talked about spatial and temporal locality, and how the various ways analytical studies have shown how this typically performs with real code. We talked to the characteristics of memory systems. We talked about performing models of a multi-level memory hierarchy. We spent a fair amount of time on two-level memory access and also alluded to the fact of having multiple level access. Then we got into more details about the memory hierarchy of trying to be thinking about the cost and performance characteristics and how we will go about making a decision, what we wanted to be doing for a specific implementation. We talked about typical members of the memory hierarchy. We went into details about the IBM Z13 memory hierarchy of what they did with their implementation. And finally, we talked about the design principles for a memory hierarchy. All right, well, thank you very much. That finishes our lecture.